Okay, so the one that we said we were going to look at was it natural log of x minus natural log of 2. Okay. And we're trying to look at it at the value x equals to 2. So I can show you this both graphically and numerically. And in the first example here, let's look at numerically, okay? If we're looking at these numbers, as I approach this graph, here's the values which are larger than 2, 2.001, 2.00, 2.001, 2.01, 2.1. So these are values that would be on the right side. They're over here, just to the right, okay? What would you expect if you covered up this bottom half? What does this look like it's approaching? What number looks to be emerging from there as we get closer to 2? It looks like 0.5 is the number that is coming up. So that's what we'd probably think to start off with. What if we go from the other side, numbers which are less than 2? So 1.9, 1.99, we keep moving. What number appears to be coming out of that? 0.5. As we get closer, both sides are trying to tell us it's 0.5. So if we try to zoom in a bit more on the graph, you'll see that the graph actually looks very nice. It's not defined at x equals 2, but it's a nice smooth curve. If I wanted to look on the right side of the graph, it's going to be, let's see here, maybe I can make these limits come out a little bit better. -2 and 2. Yeah, so at x equals to 2, you can see by the picture it equals a half, even though it's not defined there. But because the left side approaches nicely as close as I want to a half, and the right side also agrees, we would say this limit does exist. Okay? It's not defined there, but the limit does exist. We can get as close as we want, and we'll still end up on a half. Okay? So try the same thing with the next example and see what you can come up with for 4 times x minus 1 over x squared minus 1 as x goes to 1. See what you come up with. Okay, so I'll put this one into that same applet, which is here, and it was 4 times x minus 1 divided by x squared minus 1. And we were looking at the limit as x approaches 1. Okay, so here you can see that there is some weirdness happening at this graph. Can anybody figure out where the limit may not exist on this graph? Is there a problem that we cannot resolve? What do you think? Yeah, that asymptote could cause a big problem because one side of this asymptote is trying to tell me over here on the left that it would be negative infinity. The other side is trying to tell me it would be positive infinity. It just keeps getting bigger and bigger and further apart. There is no way to resolve that limit at x equals -1. That is a problem. The limit would not exist there. Okay? But if we look over at +1, right here, even though it is not defined because we would divide by 0, you can see it's a nice smooth curve. There doesn't appear to be any oddness or weirdness happening. And as I approach from values which are larger, I go from this side. As I get closer and closer, I approach the number 2. And same thing here. As I approach, it comes close to the number 2. Okay, so we can also verify it if you look at the numbers in the table. Those numbers there, they get closer and closer to 2 as I get closer and closer to 1. Okay. So again, it's not defined at x equals 1, but the limit does exist in this situation. Question? So if you're looking at the graph, then what you're looking for is you're looking for it to be a nice, smooth piece that doesn't indicate any problems. The picture looks like there's no problem. So if I looked here near +1, that's where the limit is, does there appear to be any problems as I get close to 1? No. So I can even zoom in. It's a nice, smooth curve. From my point of view here, it doesn't look like there's any problem. If I was to try it the other way, though, and say, what about -1? Well, there's huge problems here. Because look at that, right at -1, that graph keeps diverging, getting further and further apart. Those pieces do not meet up. Okay? So in this instance, we'd say at -1, the limit does not exist. We can't fix that. There's no nothing we can do about it. It becomes infinite there. So it's possible in your TI-83 as well to do a table. So other than the graph that I've got there, let me show you how to do a table for your TI-83. So here's the steps that you'd follow, and I'll come around and see how you're doing with it at limit as x goes to 0. And this, by the way, is you will want to try this. It will make your homework go a lot easier if you do it this way. So in y1, you're going to enter this function, x divided by square root x plus 1 minus 1. And we're looking at the limit as x goes to 0. Okay, so that function goes into your calculator as y1, and then we're going to use the table method to do this. So you select table set in your TI-83, and then you have to move down to independent and select ask. Otherwise, it tries to automatically fill it, and we want specific values here. -0.1, -0.001, -0.0001. So you have to say ask so that it asks you for the value. Okay, the next thing you're going to do is hit the table button, and what you'll see is an empty table waiting to be filled. If you put in this value, the calculator will put out the y values automatically. So I'll come around and just give you guys a hand with that in then. So if I'm using my TI-83 to do this, the best thing I can do is mimic a TI-83 for you in that applet that I've got. So let me bring up that applet one more time. Okay, this time the function I'm looking at is... Sorry, this time the function I'm looking at is x divided by square root x plus 1 minus 1. So this is the picture you would see, and we're trying to evaluate it as it gets close to 2. So this applet, it's 1, right? As it gets close to 1. Do I have it entered in properly? Let me just double check. 0, sorry. Third time is a charm. 0. Okay, so as I approach 0, again, you can see from the picture that the graph looks like it's together, that there's no problems happening there. But one thing, when we look in the table can also confirm for us those values. What does the table appear to be approaching as I come from one side and the other? 2. So we would say we could use the table as well. The table is kind of confirming our suspicion that as we get closer to 2, the value gets closer to, as we get closer to 0, the value is closer to 2. Okay, the other one, sine x over x, as x goes to 0. I will fill this one in here. You can do it on your TI-83. So sine x over x. Again, at 0, you'd be dividing by 0. That's a problem. But if you look at it, you see that curve. There's nothing crazy or strange happening on that curve. If you ask somebody in grade 11 what they think the value is at 0, what do you think they would tell you? Based on that picture at x equals 0, what would a grade 11 student tell you? It's equal to 1. Yeah. So it's right here. That value at 0 looks like it's 1. Aside from the fact that we divided by 0. And you can see in the table, closer I get to 0, it's actually so close to 1 that the computer has rounded it. Okay? So, do people need another minute to fill in their tables? Hands up if you need a minute. Okay. So, we've just vaguely talked about the limit existing because it looks like a nice graph. Here are some examples of when you may see the graph does not exist. Okay? So first of all, in this picture, when I look at it, this one here, if I look at it coming from values smaller than 0, it would imply that the value is 0. Okay? If I look at it coming from this side, it's trying to tell me the value I would choose is 2. Okay? Those two things do not agree. So as I get closer and closer, there becomes more confusion. Out here, no problems. As I get closer, though, there's some strange behavior. The graph jumps. So because of that jump, as I get closer, that answer starts to diverge. That limit would not exist there. We will talk about formally what limits, exactly a limit has to be, but the pictures are always easier to understand in calculus than a lot of times the definitions. So for our first scenario there, if we have a jump where the graph breaks apart, that limit will not exist. Okay, in the next example, as we get closer to 0 here, now it's tempting for us to say, oh look, they're going to meet up eventually. Where will they meet up? Yeah, the correct answer is never, because they're going up to infinity. So that means maybe I pick the value 0.01, okay? And it says, oh, no problem, that's 100. Then I pick 0.001, and it says, oh, that's 1,000, 0.0001. That's 10,000. It keeps getting bigger and bigger. It's not agreeing on any particular number. It just keeps getting bigger and bigger and bigger. So the limit does not exist when things become infinite. So for these infinite ones, they would not exist either. Okay. Now, sometimes graphs, especially when we introduce trig stuff, sometimes they go wonky because of the oscillation, the repeating periods. So this graph here, when it's oscillating, the limit would not exist. What I can do to show you here how this is true, I'll show you. You just have to hold your breath a little bit because, not hold your breath, take a deep breath and relax, yeah. Because, again, conceptually thinking is a little bit tougher, but here's why this limit does not exist specifically. As I approach 0, I'm going to start picking numbers to show you that are getting closer and closer to 0. Okay, so for example, to start, I'm going to pick 2 divided by pi. Okay, that reciprocal would give me a value of 1 when I stick it in, right? Pi over 2. Are we with me so far? Because if I put this in here, that'll be the sine of pi over 2. That's 1. Okay? The next place I'm going to pick is going to be 3 pi over 2. Okay? Where would I be now? Negative 1. Okay. The next place I'm going to pick is 5 pi. Or sorry, 2 over 5 pi. Where would I be this time?
1.
Yeah, sine of 5 pi over 2. This would be at 1. These numbers keep getting closer and closer to 0. But the values keep going 1, negative 1, 1, negative 1, 1, negative 1. They keep bouncing back and forth, even though the denominator keeps getting larger. So denominators that keep getting larger is going to make this fraction smaller and smaller and smaller. As these approach 0, the limit keeps flip-flopping back and forth. So the limit does not exist because it keeps bouncing. It can't decide where it should go. Okay? But for our purposes, for the most part, it's just sufficient that you know an oscillating graph would not have a limit that existed. Okay? Now, so just to give you an idea where we're headed, let's take a look at this graph, and we'll take a look graphically and algebraically. This is the absolute value of x divided by x. So you can put it into your TI-83. I am going to put it into that applet.